We have a worked example right here. This is a figure that represents a potentiometer circuit. In this potentiometer circuit that is being showed, we have a slide wire AB, and we are being told that this slide wire AB has a length of 100 centimeters right there. This slide wire also has a total resistance of 15 ohms. This 15 ohm slide wire is connected in series with a resistor of 5 ohms, which resistor is having a certain switch over it, switch K1, which is capable of bypassing it when K1 is closed, and this is also connected to a 3-volt cell, or internal resistance is negligible. Now we are being told that when K1 and K2 are open, it means that when this switch K1 and that K2 are open, that the balance length, when we slide this jockey along this slide wire, the galvanometer will show no deflection when AJ is 75 centimeters. Likewise, when K1 is open but K2 is closed, the galvanometer will show no deflection when the balance length is 65 centimeters. With this kind of information now, we are being required to answer these following questions. Find the value of the EMF. Now the EMF they are talking about here is actually that one. This is in the secondary circuit. In the secondary circuit, we're having a cell whose EMF has been dubbed E, and this cell has an internal resistance R. Our value here is to find E, the EMF of the cell in the secondary circuit. Remember, this is the primary circuit, this is the secondary circuit. And of course, it also has an internal resistance R that we do not know yet. But the first question is telling us to find the value of E. So we'll go ahead and calculate the value of E, the EMF of the cell in the secondary circuit. But to calculate the value of E, the EMF in the secondary circuit, we need to take advantage of this information that has been given to us to be able to find the things that we do not know. So we shall start from a point of information we know to help us get information we do not know. Now we all know that when potentiometer circuits are connected, such as this one, when we slide this jockey along this slide wire AB, we are going to reach a point whereby the galvanometer shows no deflection, and when the galvanometer shows no deflection, that's the point where we attain the balance length. At balance, the potential difference across the balance length, AJ, is equal to the potential difference across everything in the circuit. Now when the question tells us that when K1 and K2 are open, first of all, when K1 is open, it means that when current is coming, it is having to go through that 5 ohm resistor. It means this 5 ohm resistor is in the primary circuit when K1 is open. When K2 is open, in this case, it means that this 10 ohm resistor is redundant as far as the secondary circuit is concerned, because the circuit here is incomplete. So meaning that when it is, if I am to redraw this when K1 and K2 are open, this is how this would look like. So when K1 is open, it means that this 5 ohm resistor is in the circuit, and when this K2 is open, it means that this 10 ohm resistor is redundant. So if I'm to redraw this is how it would look like. There's nothing here, so we only have this value E and the internal resistance R of this primary cell. And so we have this slide wire AB that is 100 centimeters long, and it is having a resistance of 15 ohms, and then we are having this 3-volt cell in the primary circuit. So this is exactly the correct interpretation. And now we are being told that when K1 and K2 are open, AJ is 75 centimeters. So it means that when this and that are open, the balance length is 75 centimeters. And if the balance length is 75 centimeters, it means that the potential difference across that balance length is going to be equal to the potential difference across what is in the secondary circuit. In simple terms, if we were to look at the RE model diagram, it means that the potential difference across this AJ is going to be equal to the potential difference across the cell in the secondary circuit. So it means for us to be able to find the value of E, which so happens to be the EMF of the cell in the secondary circuit, we simply have to find the potential difference across that balance length. Finding the potential difference across that balance length means that we need to find the potential difference, PD per unit centimeter, of that slide wire AB. When we get the PD per centimeter of that wire AB, Then we multiply it by the balance length, in which case this balance length here we are being told it's 75 centimeters, and that is how we will be able to find the potential difference across that portion of the slide wire. And definitely that is how we will be able to know the PD in the secondary circuit. So we will begin our working. First and foremost, we will begin by seeking to find the PD per unit length of the slide wire AB. Now, just like we had done in our previous session, to find the PD per unit length, we first find the amount of current flowing in the primary circuit. So to find the amount of current flowing in the primary circuit is going to be equal to V over R, and definitely our V here is 3 volts. So it's going to be 3 divided by the effective resistance in the primary circuit when K1 is open. Of course, we have 5 ohms. We add that to resistance of the wire AB, which is 15 ohms according to our question. It is 15 ohms. So this is 15 ohms. So we add this to 15 ohms. And here we will have 3 over 20. 3 over 20 amperes, that is the amount of current that is being given off by that primary circuit. So we'll go ahead and find the PD per unit length of wire AB. So to find PD per unit length, or in this case since it's in centimeters, PD per centimeter of the wire AB is going to be equal to the current I that is going through that wire, which so happens to be the primary current, multiply that by the resistance per centimeter. And the primary current in this case is going to be 3 over 20, multiply that by the resistance per centimeter. Now the resistance per centimeter is going to be gotten by getting the resistance of the whole wire, divide that by the length of the wire in centimeters. So the resistance here is 15 ohms. Divide that by the length of the entire wire, which so happens to be 100. So it means the resistance per centimeter is 15 over 100. So we will go ahead here and we get our PD per centimeter of the wire AB. And in this case, our PD per centimeter of the wire AB is going to be 9 over 400 volts per centimeter. Now that we have our PD per centimeter, which is 9 over 400, remember the question requires us to find the EMF of that cell E. And to find the EMF of that cell E, remember that when K1 and K2 are open, the balance length is 75 centimeters. And if the balance length is 75 centimeters, according to the principle of the potentiometer, that balance length, the potential difference across that balance length, is equal to the potential difference across that cell E. Since K2 is open, it means that this resistor is redundant, it's not in the circuit. So the EMF of that cell E is equal to the PD across that balance length AJ. So it means if the balance length AJ is 75 centimeters, and now we have the PD per unit length of this slide wire. So to get the potential difference across that balance length, this means you're going to get the PD per centimeter of this wire, multiply it by the length, the balance length, which so happens to be 75 centimeters, so that we're able to get the PD across that balance length AJ. And when we get the PD across that balance length AJ, that potential difference is definitely equal to the EMF of that cell, and that is how we will be able to get the EMF E of that cell in the secondary circuit. So to go ahead and find that, we'll just go ahead and multiply the potential difference across the balance length AJ when K1 and K2 are open is going to be equal to the EMF of the cell in the secondary circuit. So this PDF is gotten by, it is PD per unit length, multiply that by the balance length, should be able to give us the EMF. Now the PD per unit length here we got was 9 over 400, which is 9 over 400. Multiply that by the balance length according to our questions, which is 75 centimeters. This is supposed to be giving us the EMF of that cell. And definitely when we multiply there, the EMF of that cell there is going to be 1.687 volts. And that is the EMF of the cell. This answers the first part of the question. Now that we have the EMF of that cell E, now we're being asked to find the value of the internal resistance R. Now, of course, we are being required to find the internal resistance of that cell R right there. Now here again, when we are still, our question says that when K is open and K2 is closed, the balance length is 65 centimeters. Now the 65 centimeters we are talking about, AJ, is the balance length when K1 is open. This is open. Of course, when K1 is open, it means that the 5 ohm resistor is still in the circuit. And if the 5 ohm resistor is still in the circuit, in the primary circuit, it means that the PD per unit length is still the same as before, because even in our previous number, K1 was still open. So the PD per unit length is as before. And so when K2 is closed, it means that it is going to bring this 10 ohm resistor into the circuit. So in other words, when K2 is closed, it means that this and that, this secondary circuit has now attained the 10 ohm resistor. The 10 ohm resistor has now become part of the secondary circuit now. It's no longer redundant when K2 is closed, when this switch is closed. Now, this means that AJ is going to be equal to 65 centimeters, the balance length across these two elements in the secondary circuit. And so to be able to find the internal resistance R, it means that we are going to calculate this number like we are dealing with only this secondary circuit. Remember, at balance length, no current is flowing through the galvanometer because the galvanometer is deflecting 0. So in simple terms, it's like when we are trying to find when this comes in contact, it's like we ignore this upper part and we look at this cell and that, and we seek to find the internal resistance of this. If I'm to remodel this diagram, this is how it would look like. K2 has been closed. The galvanometer is, this is the slide wire up here. K2 has been closed, so it means that the 10 ohm resistor has come into the circuit, and we know that current flowing out of this cell is simply coming through like that. No current is going through the galvanometer, it's because it is deflecting 0. In simple terms, when the galvanometer shows no deflection, the potential difference across the slide wire is going to be equal to the potential difference across that 10 ohm resistor. So that is where we're going to start from. That we know that is a piece of information that we're going to use to help us find the internal resistance of this Downer circuit. And of course, to find the internal resistance of this Downer circuit, since this is a cell whose an EMF E whose internal resistance is R, it's not negligible. It means that E, we shall use E is equal to I into R plus R. Now we know that E is the same as V is equal to capital I, which is the current, times R. R being the effective resistance, but now since here the effective resistance includes an internal resistance also, it means that we are going to treat the internal resistance is always treated as though it is in series with the effective resistance of the external circuit. That's why we say R plus capital R. We covered this in our previous videos. So now E is equal to capital I into R plus R. This is current going through the secondary circuit. Now, what are we interested in? We want to find the small r, the value of the internal resistance of that cell. So the EMF E, which so happens to be, we got the EMF in our previous question. We got our EMF as 1.687. So 1.687 is going to be equal to the current flowing through the secondary circuit. Multiply that by the resistances. The resistance in this case, we have 10 ohms plus the internal resistance R that we want. Now here we do not know the current flowing through the secondary circuit out of this. So we make IS the subject of the formula. This becomes 1.687, divide that by 10 plus R. Now this is the current that is flowing through the secondary circuit that is coming out of here, and it is going through that 10 ohm resistor. Now remember, I said that at balance, that the potential difference across this slide wire is going to be, which is 65 centimeters, is going to be equal to the potential difference across the 10 ohm resistor. So this is the concept we are going to use to help us find this value of R, the internal resistance R. So we know that the PD across AJ, which AJ so happens to be the balance length, is going to be equal to the potential difference across the 10 ohm resistor. So what is the potential difference across AJ? The potential difference across AJ is going to be given by the PD per unit length of AJ, multiply that by the balance length, is going to be equal to the PD across the 10 ohm resistor. Now it means it's going to give us the current that is going through the 10 ohm resistor times the resistance of the 10 ohm resistor. Now what is the current going through the 10 ohm resistor? If you look at our diagram here, of course the current that is going through the 10 ohm resistor is the current that has been produced here, which so happens to be this. So it means that this is going to become IS. The current going through the 10 ohm resistor so happens to be the IS, the current in the secondary circuit. So we are going to put this expression to substitute for that. If I may continue with this, what's our PD per unit length? Our PD per unit length, which we are calling K, we got it before as 9 over 400 volts per centimeter. When we multiply that by the balance length, now the balance length here, according to our question, we were told that the balance length AJ is 65 centimeters. So it is the PD per unit length times 65 centimeters that is going to be giving us the current that is going through that 10 ohm resistor, which so happens to be 1.687 over 10 plus R. Multiply that by the 10 ohm resistors, which so happens to be 10. So from this expression we are able to get our value of R. So that is the internal resistance of that. Of course here I have made R the subject of the formula in this expression, and that's how I've arrived at 1.54 ohms. That is the internal resistance of the cell. One more bit of this question. Now we're being required to find the balance length when K1 is closed and K2 is open. When K1 is closed and K2 is open, still it means we're going to move this jockey along the slide wire AB up to a point whereby the galvanometer shows no deflection. At that point when the galvanometer shows no deflection, the balance length, potential difference across the balance length will be equal to the potential difference across this EMF. Now we got the EMF of that cell in part 1 of the questions. We got the EMF of this cell. So it means that the EMF of this cell should be equal to the potential difference across the balance length, which is gotten by getting the PD per unit length times the balance length. But then now remember that when K1 is closed, when we close switch K1, it means that the 5 ohm resistor is no longer in the circuit. It is redundant because the current that is being produced here is going to bypass that 5 ohm resistor, and the current will just bypass it like that. So what does that mean? It simply means that the amount of current being drawn out of this 3 volt cell is going to change because the 5 ohm resistor is no longer in the circuit. And if it is going to change, it also means that the PD per unit length here is also going to have to change. So it means that if it's going to change, it means we're going to first find the new PD per unit length. When we get the new PD per unit length, then we are able to find the balance length. Since we know that at balance, since this K2 is open and this thing is redundant, it's not in the circuit, it means this EMF of the cell, which we got in the first part of the question, should be equal to the potential difference across that balance length, which can be got by getting the PD per unit length that we are going to calculate right now, multiply that by the balance length L, which is required of us in this question, as it reads that find the balance length when K1 is closed and K2 is open. So we will begin our calculation first by finding the new PD per unit length as a result of looping or bypassing this 5 ohm resistor. So we'll begin by first finding the amount of current that is drawn up. So our new current, IP, the primary current, is going to be equal to V over R. That is going to give us the PD, which is 3. Divide that by the effective resistance. Now, of course, the effective resistance now is 15 ohms. This 5 ohms is no longer part of it since it's being bypassed. So it's 3 over 15. And definitely 3 over 15 gives us 1 over 5 amperes. Now that we have that this is the amount of current going through that, so it means that our new PD per unit length, PD per centimeter, is current I that is going through that wire, which so happens to be our primary current, multiply that by the resistance per centimeter of that wire. So this is going to become our new current, which is 1/5. Multiply that by PD per centimeter. Multiply that by resistance per centimeter. Our resistance, the resistance of this wire is, according to our question, 15 ohms. So it's going to be 15 ohms, divide that by 100, because the entire wire is 100 centimeters. So we shall end up with our new PD per centimeter being 3/100 volts per centimeter. Now that we've got the new PD per unit length as a result of us closing wire K1, so we can go ahead and find the new balance length when K2 is open now. So we know that when K2 is open, the new balance length is that the EMF of this cell should be equal to the PD across that balance length. So it's going to become our PD across AJ. We get it by the PD per unit length, multiply that by the balance length, is going to be equal to the EMF of that cell. Now we got the EMF in the first part of the equation as 1.6875 volts. Our PD per unit length in this case is going to become, is what we got. Our PD per unit length is 3/100. Multiply that by the balance length, which is required of us in the question, is going to be equal to 1.6875 volts. So our new balance length therefore is going to become, so our new balance length is definitely that, and that's. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.